So 6.3 is going to introduce you to a couple of new identities. The identities we're going to start with and then build off of are called the composite identities. So look at the word composite. We know what identity means, right? It's an equation that's true for all values in the domain. They're mathematical synonyms. What does the word composite mean? Whether it's in a math or an English context. Composite. Compose. What's that? Well, what does compose mean? To combine. Yeah, to make, right? Like musical composers. They made music. Compost. Is that a different word? Yeah, that's a different word. Compost, yeah. So, thank you. If you don't memorize your identities, you might be making compost as you go through some of the proofs. But hopefully that doesn't apply to you. So that's what composite means. It means to combine. And so that's what these identities are going to do. So let's say that we had the expression cosine of x plus y. What does x plus y represent? An angle or a ratio or something else? It's an angle. Good. But notice it's not just like cosine of x or cosine of y. It is an angle that is composed of two other angles, x and y. And in this case, we're combining them by adding them together. Would you like to guess how we can simplify that? Do you feel an urge to distribute the cosine and call it cosine of x plus cosine of y? Do you have that urge? Sure. You don't have to have the urge. Okay, I don't. Well, good, good. Same thing with smoking, right? You don't have that urge. Good, good, good. Both of them are bad. Smoking and distributing the cosine inside are both bad. Okay, so this is not equal to cosine x plus cosine y. All right? Very similar when we had the natural log of a plus b, that was not equal to the natural log of a plus the natural log of b. Okay? So in general, you cannot distribute a function inside itself. Okay? There's not a way to do that in general. With natural log of a plus b, there's no way to do it. But there is hope for something like cosine of x plus y. The bad news is it's not as simple as distributing. But there is a way to express cosine of the angle x plus y in terms of single x and single y. And I'm going to introduce that to you right now. So here are called the composite identities for cosine. All right? And here they are. There's two of them, and we'll combine them here in just a second. Cosine of x plus y, the composite angle x plus y, is equal to cosine of x times cosine of y, and then minus sine of x sine of y. So that's what it's equal to. It's not equal to cosine x plus cosine y. It is equal to this. And similarly, cosine of x minus y, if you have a new angle that's composed of the difference of those two, it's not cosine of x minus cosine y, but it is equal to cosine x cosine y plus sine x sine y. So does anyone see a pattern there that would help you memorize that? No one sees a pattern? We as humans are good at recognizing patterns. They're both written in Times New Roman font and black ink. Very good. Okay? No. What do you notice about here? If we got a plus sign over here, it becomes subtraction. And if we have a subtraction sign here, it becomes addition. So with the cosines, the sign does change, the SIGN sign. So if you have two angles that are added, you're going to subtract those two. And if you're subtracting two angles, you're going to add them. What else do you notice? They both start with what? Cosine and end with sine. So if you want to think of cosine as being selfish, it kind of helps. Cosine is selfish. What do selfish people say usually? Me. They're me monsters, right? Me, not you, me. So cosine being selfish, cosine of x plus y, guess what it is? It's cosine. Cosine insists on going first. Me go first. It's my identity. See, it's got my name on it, cosine. So it's me. Cosine of the first, cosine of the second. And sine is selfless. Sine's like, whatever, cosine. Have it your way, you me monster. I don't mind going second. There's plenty of x's and y's for everybody. So then sine, who is selfless, goes second. So if you can remember that, cosine is a me monster, a selfish me monster. Sine is selfless. Cosine is me, and then you. All right? But me first. Stupid cosine. Okay, now you can combine these two in one identity. If you think 1 is less than 2, it's easier to memorize. Cosine of x plus or minus y, that's how we read that, is equal to cosine x cosine y, me, and then, what is that? No, that's minus plus, sine x sine y. So if it's plus minus here, it becomes minus plus here. And that indicates that the sign, S-I-G-N, does what? Changes. Okay, cool. So what this allows us to do, this is the important part, it allows us to express a composite angle, that is the sum or the difference of two other angles. It allows us to express it in terms of those two smaller angles. All right, so why would this be useful? Good question. We can expand the power of the unit circle. It's already pretty useful. But let's look at example 1. It says to find the simplified exact value of cosine of 15 degrees by finding two angles from the unit circle that either add up or subtract to give us 15. Hang on. Time out. You're throwing radian angles at me. And what is our angle in? Degrees. So you're already doing the more challenging, fun type. Okay, it's easier to start off in degrees, typically. Now, is 15 degrees on the unit circle? No. It's on the unit circle in the sense that all the angles in the whole wide world are there. But is it one of the angles that we memorized? No. Okay. So, Tyler, you're very optimistic this morning. I like it. So here would be the angle 15 degrees. Now, because it is very small angle off the positive x-axis, the cosine of 15 degrees should be closer to what? 1 or 0? Should be closer to 1, right? Remember, cosine measures the width of your triangle, and sine measures the height. Okay? So this should be something really, really close to positive 1. But what is it exactly? I don't know. The calculator will tell me. But if I ask you for the simplified exact answer, the calculator won't give you that. So this is where the composite identities come in. If you can find two angles from the unit circle, for which we know sine and cosine and all the other trig values, if I can find two angles that either add or subtract to give me 15 degrees, I could then use the composite identity to write it in terms of those two angles. So now in degrees, Tyler, what are two angles that add or subtract to give you 15 from the unit circle? In degrees. It's supposed to be easier in degrees. I'll come back to you for the radio. 45 and 30. 45 plus 30? 45 minus 30. There you go. Now, why did you not choose 16 and 1? 16 minus 1 is 15. 16 and 1 are not on the unit circle. So 45 and 30 both are. So would everyone agree then that 45 degrees minus 30 degrees is 15 degrees? Yes, good. So now what we could do is we can expand it using the composite identity. And because it's cosine, is cosine selfish or selfless? Cosine? He must show you a different side than he shows the rest of the world. Cosine is selfish. Me, right? So if it's cosine of 45 minus 30, it's going to be cosine. So it's cosine of the first times cosine of the second. Me. And then, what happens to the SIGN sign? It changes. So if it's minus there, it becomes plus. And then it's selfless sign. So then it's just sine of the first times sine of the second. Laid back, chillaxed sign. So notice we preserve the order of the angles. Cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second. So those should be equivalent. Now, why is that useful for us? Because I can now, from the unit circle, replace each of those four trig functions with their ratio. So what is cosine of 45 degrees? Square root of 2 over 2. Cosine of 30 degrees, or pi 6? Square root of 3 over 2. Is your iPad charged down? Sine of 45 degrees, square root of 2 over 2. And then sine of 30 degrees, 1/2. Okay? So now we're going to simplify that. If you just multiply straight across, you're going to get the square root of 2 times the square root of 3, which is what? In the first term, multiplying across. That's the square root of 6, right? Remember, you can multiply radicals together by putting them under the same radicand. And then in the bottom, 2 times 2, that's 4. And in the second term, square root of 2 times 1 is square root of 2 over 4. And now to combine two fractions, we need a common denominator. Do we have one? We do. So now we can call this the square root of 6 plus the square root of 2 all over 4. And that's as simplified as this one gets. We can't combine those two radicals and call it the square root of 8 because they're unlike radicals. So there is the then simplified exact value for cosine of 15 degrees. Now we will verify that on the calculator. So I'm going to go to degree mode because I was in radians, and we'll type in cosine of 15. And the calculator should give us a positive number that's really close to 1, right? 0.965. Yeah. And now we'll type in underneath there, oops, I don't want to do a stat plot. We'll type in the square root of 6 plus the square root of 2, and then we'll divide it by 4. And if we did it correctly, these two numbers should be what? Same or different? Same. Same. Very good. So if you typed in cosine of 15 on your calculator, let's do that again. That was fun. And I asked you for the simplified exact answer. Can you just hit math, enter, enter? Will that convert it back? No. Because what type of number is the square root of 2 plus the square root of 6 over 4? It's a fun number, yeah. But it's also a non-terminating, non-repeating decimal known as a irrational number. Yeah, and your calculator doesn't convert those back to radical form for you. So there you go. There is enough motivation, hopefully, the only motivation you'll need to determine or why these identities are important. Now, are those the only two angles that add or subtract to give you 15 from the unit circle? No. So let's see if we can do it again, but with different angles. Since 15 is so small, we're probably going to be subtracting, right? So what are some other angles that subtract to give you 15? 60 and 45. Let's choose some crazier ones from a different quadrant. How about 315 minus 300? Are those both on the unit circle? Yeah, they are. They're both in quadrant 4. Let's choose some different ones because those have positive cosine values. Well, those will work. Those will work. Let's go ahead and expand it now using identity. Cosine, selfish or selfless? Selfish, right. I don't even like talking about him because he's just so selfish, but we have to. Cosine of the first, cosine of the second. Me. And then change the sign, and then sine. 315, sine of 300. So there's the first step, and I would need to see both of these. I would need to see the angles that you're using and then the expansion. And now it's unit circle time. Everyone's favorite time. What is cosine of 315? It's the same as 7 pi fourths, so it's square root of 2 over 2. Cosine of 300, it's the same as 5 pi thirds. That is 1/2. Sine of 315, that's the same as sine of 7 pi fourths, which is negative square root of 2 over 2. And then sine of 300 is the same as sine of 5 pi thirds, which is negative square root of 3 over 2. So if you simplify that, what's a negative times a negative? Positive. Whew. I was wondering how we're going to get a positive when that first one was negative, but I multiplied wrong in the bottom over here. 2 times 2 is 4. So then I get the square root of 2 plus the square root of 6 all over 4. And because addition is commutative, it ends up being the exact same thing that we got over there. So it doesn't matter which angles you use, as long as they do in fact add up to or subtract to give you 315 degrees. If you use the identity correctly, you'll get the same answer. Pretty nifty. Pretty nifty. Okay, so here's the upshot of that. We can now expand the unit circle to find exact values of any angle that is a multiple of 15 degrees. It doesn't have to be just 15 degrees. Of course, 15 times 2 is 30. That one's already on there. 15 times 3 is 45. Any multiple of 15 degrees, we can find two angles that add or subtract to give us that number. And of course, 15 degrees is what in radians? Pi 12. Because 30 degrees becomes pi 6, and half of 30 is 15. Half of pi 6 is pi 12. So now if you ever see a radian angle, something pi 12, you can find two angles from the unit circle that'll add or subtract to give you that angle. So we did it with degrees to start with because it was supposed to be easier, but now we're going to shift to radians. So anything pi 12 is going to be doable. All right? Let's try it out. Example 2. Find the simplified exact value of cosine of 7 pi 12. Well, first of all, I'm giving you the instructions here by finding two angles that add or subtract. I'm not going to in the future. So if I ask you for the simplified exact value, how are you going to know to use the composite identities? Because there'll be other angles later on called half-angle identities. Well, how do you know? If you look at it, it's something pi what? 12. And anytime you see something pi 12, you know it's going to be a multiple of 15 degrees. So you know you're going to use the composite identities. So let me walk you through this. It's a little bit more fun when it's in radians, because our angles on the unit circle have different denominators, right? Pi 6, pi thirds, pi fourths. And when you add or subtract two angles with different denominators, you need to get a common denominator. So how can you then find two angles that add or subtract to give you 7 pi 12? Well, number one, you could do trial and error. Get a common denominator and see if when they add or subtract give you 7, or do it a little bit smarter. Multiply 7 by what? You want to convert it to degrees now? Is that what you, no, I don't want to do that either. Here's the easy way to do it. If you can split up the coefficient of pi 12, in this case 7, into the sum or difference of two numbers that have a common denominator with 12 other than 1, it will work. Okay? So you don't want to call 7 pi 12 6 pi 12 plus 1 pi 12. Because 1 pi 12, now you're stuck. Well, what are some other numbers that add or subtract to give you 7? 2 and 5. Okay. Well, 2 pi 12 is okay because 2 and 12 have a common factor of 2. But what about 5? Do 5 and 12 have a common factor other than 1? No. So 3 and 4 would work. Yeah, now here's why that's good. If you write 7 pi 12ths then as 3 pi 12ths plus 4 pi 12ths. 3 and 12 have a common factor other than 1, and 4 and 12 have a common factor. Oops, that's 12, other than 1. And because of that, you can do what with those two fractions? You can simplify them. All right, so that's the key. 3 pi 12 simplifies to pi fourths, and 4 pi 12 simplifies to pi thirds. So if you pick two angles that have a common factor with 12, other than 1 or negative 1, you'll be able to simplify, and those two angles should be on the unit circle. So there you go. What's pi fourths plus pi thirds? 7 pi 12. And you don't have to worry about getting a common denominator. And now that we have it expressed as the sum of two angles, now we can use the identity. So it's cosine, cosine, me, cosine of the first, cosine of the second. What happens to the plus sign? It becomes minus. That's the price of being selfish. Right? It's going to cost you. You have to change the sign. And then sine of the first, sine of the second. And once you get to here, then you should be in the clear, right? You're rounding third, heading home, the ball's in the outfield, you're going to score. Assuming you still know the unit circle, which I don't know why anyone would forget it, right? Today I'm going to unlearn the unit circle. No! Change your plans. Sweep out the garage or something instead. Cosine of pi fourths, square root of 2 halves. Cosine of pi thirds, 1 half. Minus sine of pi fourths, square root of 2 halves. Sine of pi thirds, square root of 3 halves. Now when you multiply across, you're going to get the square root of 2 over 4 minus the square root of 6 over 4. And now your final answer is the square root of 2 minus the square root of 6 over 4. Which is a different number than what we just previously got because now they have different signs. Is that number going to be positive or negative? Should be negative, right? Because the square root of 6 is bigger than the square root of 2. So that should be less than 0. Is that reasonable? Where does 7 pi 12ths live? It lives in quadrant 2. Yeah, where cosine is negative. There you go. Now, if you use the composite identities, you're going to notice quite often that you end up with some type of square root of 2 and some type of square root of 6 all over 4. And the reason is we're using unit circle ratios that have numerators of 1, square root of 2, and square root of 3. And that's the combinations that you get when you multiply them. But what's different is whether they're both positive, whether they're both negative, or one is positive and one's negative. That's going to be what's different. All right, let's, before we walk away to the next one, let's find two other angles. Let's try one that subtracts. So what are two numbers that subtract to give you 7 that have a common factor with 12? 8 minus 1 doesn't work because 1 and 12 don't work. How about 9 minus 2? Would that work? 9 pi 12ths minus 2 pi 12ths? Does 9 have a common factor with 12 other than 1? Yeah. Does 2 have a common factor with 12 other than 1? Yep. So this should also work. 9 minus 2 is 7, so that's the critical part. But now we can simplify each of those. So 9 pi 12 simplifies to 3 pi fourths, and 2 pi 12 simplifies to 1 pi 6. Good. And if you do that correctly, if you pick your two angles, those should then simplify to unit circle angles. And now we'll use the identity. Cosine, cosine. Cosine of the first, cosine of the second. And now what happens to the sign? Becomes plus, right? And then sine of the first, sine of the second. And now it's everyone's favorite time. Not Bozo the Clown time. There used to be a show on WGN, Chicago Superstation, the morning show, and there was a creepy clown called Bozo. And he had a variety show, and he would get kids to come out of the audience and play all kinds of fun games. A little creepy. All right, that was not everyone's favorite time. Unit circle time is the correct answer to that. So now we get cosine of 3 pi fourths, which is what kind of square root of 2 over 2? Negative, right. It's negative square root of 2 over 2. Cosine of pi 6, positive square root of 3 over 2, plus sine of 3 pi fourths is positive square root of 2 over 2. Sine of pi 6 is positive 1 half. So you do end up with negative square root of 6 plus the square root of 2 over 4. And of course, that is the exact same if you commute the terms as square root of 2 minus the square root of 6. So you get the same answer. Pretty nifty. Y'all having fun so far? Cool. All right, so we now have enough information to derive one. I had to give you the cosine one, but now we can derive sines, composite identity, selfless sign. So the way that we're going to derive this is by using this identity here. What identity is that called? That's the cofunction identity, okay? So here's how we're going to develop or invent, I guess, discover, maybe is another word, the identity for sine of x plus y. We just memorized the cosine composite identity. So if I can write sine of x plus y in terms of cosine, I can use what I previously learned. So let's do that. Sine of x plus y then becomes cosine of, by the cofunction identity, pi halves minus the angle x plus y. All right? So think of this as sine of blob. Sine of blob is always equal to cosine of pi halves minus the blob. So the angle doesn't have to be just a single letter or a single number. As long as you treat it as a quantity, it'll work. So the parentheses there are important. Now what I'm going to do is distribute the negative, and I get minus x minus y. And now what I'm going to do is I'm going to associate the first two together and the last one separately. So now what I have, by grouping them that way, after I distribute the negative, I have cosine of some angle minus cosine of another angle, right? So my first angle is still a composite identity, an angle, but I can treat it as a single unit. So now I have cosine of something minus something. So using the identity, cosine is selfish, right? So it's cosine of the first, which is pi halves minus x, cosine of the second. See that? Cosine, cosine. And now because the sign in between my two angles up here was a negative, what happens down here? It becomes positive. And now it's selfless sine's term. So now it's sine of the first, which is sine of pi halves minus x, times sine of the second. And now the last thing I'm going to do is use the cofunction identities again. What is cosine of pi halves minus x? Sine. So I have sine of x, cosine of y, plus cosine of x, sine of y. And what I'm going to do is flip those around. I'm going to keep the first term the same, sine of x, cosine of y, plus, but now I'm going to commute those two factors, which is legal. I get sine of y, cosine of x. And that, then, if I bring down the original thing I started with, that's equal to sine of x plus y. So there's the new identity for sine of x plus y. So here's what it is. Because sine's name is on the identity, right? This is a sine identity, not a cosine. The rules say that sine has to go first. Sine has to go first. His name's on the identity. But because sine is selfless, sine's going to go ahead and take sine of x. But now he's like, you know what? I already had a turn, and I'm selfless. So now guess what? Cosine, it's your turn. I'm selfless. And cosine's like, you're dang right, it's my turn. So now it's sine of the first, cosine of the second, plus sine has to go first again. Now sine of the second angle, and then cosine. So what do you notice about it? Well, the order is sine, cosine, and we flip the angles. So it's x, y here, and then yx there. So we keep the sine, cosine order, but we start with the same order of the angles, x, y, and then the second term we flip the angles. And what else do you notice about the SIGN sign? We started with a plus between the angles, and we kept it here. So the sign keeps the sign. Or as I like to say, sign, same sign. Sign, same sign. Sign, same sign. Sign, same sign. It's hard to say, but I've had a lot of practice. Sign, same sign. All right? Now, what do you imagine sine of x minus y would be? Right. Sine is still selfless. Right? That's a personality trait that is deeply ingrained inside of sine. So sine has to go first, sine of the first, cosine of the second, and then sine, same sign. So if we have a minus, it stays minus. And now it's sine of the second, cosine of the first. And if we want to combine these into one, we get sine then of x plus or minus y becomes sine of the first, cosine of the second, and what are we going to have here? Plus or minus or plus? Plus or minus, sine, same sign, then it's sine of the second, cosine of the first.
Would the problem, like this Would we have to combine them?
No. If I ask you just to regurgitate the identities, you could list them both separately, or you can do them as one. I don't care.
So like if we got y first before, or negative first before positive?
Well, see, the order does matter because subtraction is not commutative. So your first term always has to be sine of the first one, cosine of the second. In the second one, I don't care if you call it cosine x sine of y or sine y cosine of x. I prefer to keep the order of the trig functions the same. Sine cosine, then sine cosine. And then what I do is in the second term, I flip the angles. So however you want to memorize it. If you keep the trig functions first, then it kind of keeps the same idea of sine as being selfless, but he has to go first because his name is on there. So that's why I do that. It helps most people memorize it. All right, so here we go. Sine, being selfless, has to go first in each term, and then cosine is going to go second because sine lets it go second. Sine, same sign. The angles flip. It has to start, though, with the order that you're given, because if it was subtraction, subtraction is not commutative. All right, so there are patterns there to help you remember it. All right, so now we can kind of, we could do the same thing with sine as we do with cosine. So I'm not going to work through those examples. But again, any angle that's a multiple of 15 degrees or multiple of pi what? 12ths. You're going to do it the exact same way. You just use a different identity. All right, so now here's what we could do. We have not proved the composite identities yet. Those were one of the ones earlier that we just took on faith. We couldn't prove it using fundamental identities. But now, with the composite identities, we can actually prove that sine of pi halves minus x is equal to cosine of x. So let's go ahead and do that. We'll draw a line down the middle. And on the left side, I have a composite angle. I have sine of something minus something. So using the composite identity for sine, it becomes sine of the first. Sorry, cosine, that's the law. I have to go first. And now cosine goes. Cosine of the second. Sine, same sign, so it's a minus. And then it's sine of the second angle, cosine of the first. So there's the expansion. And now we have sine of pi halves and cosine of pi halves. So those are actual unit circle angles, and so we can evaluate it. What is sine of pi halves? 1. So we have 1 times cosine of x minus sine of x times, I'll put that in parentheses instead. What is cosine of pi halves? 0. And so now if we simplify, 1 times anything is itself, and anything times 0 is 0. So we end up with cosine of x. Yes. And it works. And it works. So we have another problem here. Find the simplified exact value of sine of 35 pi 12ths. Okay? I'm going to let you go for it. Try and find your two angles from the unit circle, and you know they're going to be out there because it's something pi 12ths. Find two angles that add up or subtract to give you 35 pi 12ths. And you're going to do it the same way. If you can find two numbers that add up to 35 or subtract to give you 35 that have a common factor with 12 besides 1 or negative 1, it will work. So if you're watching the video at home, no need to pause. Keep it running. Find the angles. If your angles still end up being too big, like they're outside of one rotation, that's fine, because remember, coterminal angles have the same trig ratios. So as long as the angle you're using is coterminal with one from the unit circle, you're in good shape. But if you want to keep it within one rotation, remember 2 pi is the same as 24 pi 12ths, right? 24 pi 12ths. So if you can choose two numbers that are between 0 and 24, you won't have to worry about coterminal angles. In other words, 33 and 2 would work, but 33 pi 12 is outside of one rotation. It can, but then you're going to have to use coterminal angles. Once you get it down to a single trig function, you're going to have to then subtract out a full rotation. Okay, so in other words, like if you have sine of, let's say, 13 pi 6. 13 pi 6 is not a unit circle angle, but it's coterminal with 1. So if you subtract out a full rotation, subtract out a 2 pi, you're going to get pi 6. So even 13 pi 6 and pi 6, even though they're not the same angle, because they're coterminal, they're going to have the exact same sine ratio. Okay, so expand it. First, you're going to expand it. Once you find your two angles, you have to expand it first, because you can't simplify your coterminal angles until you have a single trig function. Did anyone find two angles that added up to 35 that were less than 24? 15 and 20. Yeah, so again, you can avoid that by just choosing two angles that fall between 0 and 24. 24 pi 12 being 2 pi. Then you don't have to worry about that coterminal aspect. But I'll do yours, Will. I want to show you how that works too. All right, so now that I do that, the next step is to simplify. Okay? 20 pi 12ths will simplify to 5 pi thirds. Right? They have a common factor of 4. Yeah, 5 pi thirds, yeah. Divide each of them by 4. And then 15 pi 12ths, if you divide each of them by 3, you get 5 pi fourths. So you could have had them flipped around. Yeah. I actually wrote them deliberately in the wrong order that Tyler gave them to me, because addition and multiplication are commutative. Now we will use the identity. Sine is selfless. So it's sine of the first, cosine of the second, and then sine, same sign. And now it's sine of the second, cosine of the first. And once you get that expanded, now it's unit circle time. This is where, if you had angles then that were still outside of 0 to 2 pi, this is where you would then replace the angle with the coterminal angle that falls within one rotation. But you wouldn't do that until you get to this step. All right, so all of these fall within one rotation because we chose two angles between 0 and 24. So now we just pull them off the unit circle. So 5 pi thirds, the sign is negative square root of 3 over 2. Cosine of 5 pi fourths, negative square root of 2 over 2. Plus sine of 5 pi fourths, negative square root of 2 over 2. And cosine of 5 pi thirds, positive 1/2. Super important to be in the correct quadrant because that's going to affect your plus or minuses. So now you could go straight to your final answer because you're going to be doing this enough. You know it's going to all end up over 4. It's going to end up as positive square root of 6 minus the square root of 2 all over 4. And is that a positive or a negative number? Positive, yeah. Sine of 35 pi 12ths, well, that's outside one rotation. So if I subtract the full rotation, what's 35 minus 24? 11, right? So sine of 35 pi 12ths is going to be the same as sine of 11 pi 12ths. 11 pi 12ths falls over here in quadrant 2. And so the angle that we were actually finding was all the way around and then to that terminal ray. But because they share the terminal ray, they're going to have the exact same trig function. And of course, in quadrant 2, sine is positive or negative? Positive, which is why our answer ended up being positive. If you put negative square root of 2 plus the square root of 6 over 4? No, that's fine. That's fine. It's the same number. On a multiple choice, though, if one of them was negative and the other was positive, I would probably put the positive term first as an answer choice. All right, Will, what were your two angles to begin with?
It was 9 pi 12 and 1.
Okay, let's do that one. So 9 and 26 both have common factors of 12 other than 1. but 26 is bigger than 1 rotation. So here's how you would do this one. Once you simplify, you get 3 pi fourths. And over here, you would divide out a 2? 13 pi sixths. So you can't simplify just yet. You're going to simplify after you expand. So you get sine of the first, cosine of the second, 13 pi sixths. Sine, same sign, so plus, now sine of the second times cosine of the first. And now you're staring at cosine of 13 pi sixths and sine of 13 pi sixths. 13 pi sixths is not on the unit circle, but because it's a pi sixth multiple, it's coterminal with 1. So this is where you would maybe go off to the side if you weren't sure what it was coterminal with, and you would subtract out a full rotation. And of course, the full rotation is 2 pi, or in this case, 12 pi sixths. And that gives you pi sixths. So even though, again, 13 pi sixths and 1 pi sixth are different angles, they have the exact same trig values because they have the same terminal ray. So this would just then require that one extra step. You would replace that with cosine of pi sixths, and this one with sine of pi sixths. And once you do that, now it's unit circle time. So you'd end up with square root of 2 over 2, square root of 3 over 2, plus 1/2, and negative square root of 2 over 2. And you still end up with the square root of 6 minus the square root of 2 over 4. Same answer. Yes?
Could you just simplify to within 1 rotation, like from the very beginning?
Yes, very good. That's actually what we kind of did up here. If you want to take, if your angle to begin with falls outside 1 rotation, you can cut that down 2 size and call it 11 pi 12ths to begin with. Now, you'd have to be careful, though, because you can't say 35 pi 12 equals 11 pi 12. But you could say sine of 35 pi 12 equals sine of 11 pi 12, and then you can work on finding 2 numbers that add or subtract to give you 11. Yeah, that would be simplifying on the front end, which is totally fine. I'd be totally fine with you doing that. Okay? Coterminal angles have the exact same trig ratios. All right, so I think that's where we'll stop for today. We got quite a bit done today. So memorize your identities up to now if you haven't already, because there's a lot more identities coming, and you have to memorize all of them. And if you don't have them memorized, your next test is like in 2 weeks. We're having a lot of practice between now and the next test, because there's a lot more identities, and with each new identity comes new proofs and new ways to solve trig equations.